DI also. So for that, direct load is 25 kilonewtons and bending load is 25 kilonewtons multiplied by 500. You will get in kilonewton mm. So to convert that one into Newton mm, you need to multiply that by 10 cube. So you will get that also. And another calculation we need to do here is we need to compute the allowable stress. So he has given the yield strength is 200 MPa and factor of safety is 4. 200 divided by 4 is nothing but 50 MPa is going to be the allowable stress. So once we compute the direct stress and bending stress, now since he has given the allowable stress as a tensile stress, you need to calculate what is the resultant tensile stress in the section here. So that is bending tensile. You need to consider the bending stress, which is tensile. Then of course this is going to be compressive. We need to superimpose these two. You will get a resultant tensile stress. Then take that resultant tensile stress and equate it to the allowable tensile stress, which is 50 MPa. So that is your design equation. Once you solve that equation, you will get the dimension d naught. So once you have d naught, you can compute di. Just di is nothing but d naught by 0.8 d naught. So with that, you will get the answer. So I think most of you already done this. Anyway, I will show the solution also here. So the first step is we are computing the allowable tensile stress or permissible tensile stress. That is nothing but 50 MPa. Second, we are computing the direct stress. So direct stress is P by A, which is compressive here, 25 into 10 cube by 5/4 into d naught square minus di square. So for di substituted 0.8 d naught, and if you simplify that, you will get the direct stress in terms of d naught square. So this is the value for d naught square. Then we will compute the bending moment and we will compute the bending stress also. So this is the magnitude of the bending stress is. This is the expression for the bending stress. So which is nothing but sigma b. If you want, you can denote it as sigma b, which is bending moment. That is 25 into 10 cube into 500 is the bending moment. Y max here, because we are taking the maximum stress values, you need to consider Y max, which is nothing but d naught by 2. Then this is the formula for I, that is moment of inertia of the hollow circular cross section. So now if I simplify this, I'll get this one as a bending stress. So here the bending stress is in terms of d naught cube. So then we have one compressive stress, one tensile stress. So you need to superimpose one upon another so that you will get the resultant stress. That is nothing but algebraic sum of these two. So that is going to be this is going to be the resultant stress, and it should be equal to 50, which is the allowable stress. So then if you simplify that, you will get this is the equation. So if you solve this equation, from this equation you will get d naught. So in this equation the only unknown is only d naught. So you can calculate d naught from this equation. If you calculate that, you will get d naught as 160 mm. Once you got the d naught value, then your di is 0.8 d naught. So from that you will get di as 128 mm. So like this you can solve the problem. Okay. So of course these are only simple problems. So that's why we'll call it as a simple stresses or direct stresses. So next we'll move on to the another kind of loading. That is, so far in all the problems whatever we discussed, in first problem you have only normal stress. Maybe in some problems you have only shear stress. Later we taken up one or two problems on the eccentric loading. So this is on eccentric loading. Even previous problem also on eccentric loading. Even though the load is eccentric, but the stress, the nature of stress is only normal stress. Even in this problem, you have two kinds of loads, that is bending load. Okay, so even if you take this problem also here, one compressive stress, one bending stress is there. Both compressive stress and bending stress, both are normal stress only. But suppose sometimes I have a compressive stress because of load, and here I have a torsal, twisting moment is there and torsal shear stress is there. Then the nature of the stress is different. Here, this compressive stress will try to reduce the length of the member, whereas the shear stress will try to distort the shape of the cross section. So that means they are different. Their nature of is different. One is a normal load, another one is a shear load. So therefore, if that is the case, that kind of scenario existed, we'll call that kind of loading scenario as a complex loading or combined loading. So that means because of given loading, the component will subjected to both kinds of stresses, that is normal stress as well as shear stress. In so far all the problems we solve, if you observe it, in the all the problems either you have purely have only normal stress or purely you have only shear stress. But now onwards in problems will solve the problems in which the given component subjected to normal stress as well as shear stress. If that is the situation, how we can design the component? So that means you cannot use the same design equations what we are using here for that also. So you need to follow different set of design equations when a component is subjected to combined loading. So that's what I mentioned in the coming slides. So first, when a machine component is subjected to only axial load or bending moment or torque, so what kind of the state of stress it is producing? Uniaxial state of stress. What do you mean by uniaxial? Sorry, here it is not a
unidirection, sir.
Huh?
One direction.
Uniaxial means only in one direction. The stress is acting only in one direction. That means, suppose if you take the previous problem, you have a bending stress that is only in the x direction. If you take the length direction of the shaft is x, so you have only one kind of stress, something like this. The stress is going to be unidirectional. If I take this one as a stress element, I think all of you know about the stress element, right? Did you study it or not? Nobody is responding. Am I audible to you?
Sir.
Okay, it is there. Still, class is disconnect. So what do you mean by state of stress? State of stress is nothing but the graphical representation, or you need to define all the component of the stress acting at a given particular point. We'll call it as a state of stress. That is, I think, mechanics of solids lo meer plane stress analysis chadivara leda?
Yes, sir.
Definitely it will be there. MOS1, MOS2 రెండు ఉన్నాయి కదా మీకు.
Yes, sir. Yes, sir.
Plane stress analysis definitely ఉండే ఉంటుంది అక్కడ అయితే. So plane stress in plane stress analysis, what you are studied here, I think that we are going to repeat here also. But the only thing is, for time being, the state of stress is nothing but you need to represent what are the all the stress elements acting in a component. If I take a three-dimensional body, anyway, that will come in the coming slides. So there I will tell you. But here uniaxial means only in one direction. If the stress is produced only in one direction, we'll call it as uniaxial state of stress. When the stress is produced in two directions, we'll call it as biaxial state of stress. When the stress is acting on the component in all the three directions, we'll call it as triaxial state of stress. See, don't club state of stress and either it is uniaxial, biaxial or triaxial. State of stress is nothing but if you define the completeness of the stress at a particular point, we call it as a state of stress. State of stress means you need to define what are the all components of the stress at that point. We'll call it as a state of stress. Now, if it is uniaxial state of means stress is there in only one direction, means in all other directions stress values are zero. In all other directions, the stress values are zero. That's why I'll call it as uniaxial state of stress. In case of biaxial state of stress, I have stress in two directions. In triaxial state of stress, I have stress in three directions. So anyway, I'll show those in the coming slides also in diagram. So, like I mentioned here, when you have only simply either axial load or a bending moment or simply torque, you have only uniaxial state of stress. That means the nature of stress is only in one direction. So here, in case of axial load, you have only one normal stress. In case of even bending moment also, you have only one normal stress. In case of it is subjected to a torque or twisting moment, you have only one shear stress or shear stress in only one direction. So all this comes under is uniaxial state of stress criteria. So then, so if you take any component in practice, this is only theoretical concept only. You have uniaxial state of stress. So, but in practical applications, the component may be subjected to a combination of loads. Like transmission of shaft is subjected to bending as well as twisting moment at the same time. So then in that case, so there is no uniaxial state of stress. Either you may have biaxial state of stress, or most of the practical case, if you consider all loads properly, there is a triaxial state of stress. So that means, so far whatever we saw, all those problems are related to the uniaxial state of stress. All those equations are corresponding to uniaxial state of stress. Whatever design equations you derived in those problems, they are based on uniaxial state of stress. Now we shift to our focus on either biaxial or triaxial. Mostly we'll concentrate on when the system is subjected to a biaxial state of stress, how we can define the component. So that is our focus from now onwards. So we'll use the concepts of this uniaxial state, how we design the components based on uniaxial state of stress. We'll use those concepts, and based on those concepts or by extending those concepts to biaxial state of stress, we can design the component. So that's what we are going to do in the coming problems or coming slides. Combined loading leads to complex state of stress. So here, like I shown here, uniaxial state of stress means only you have something like this. This is what we call it as uniaxial state of stress. So if I take this is a stress element, generally the stress element is shown by some square box, something like square, something like this. If I show the stress, this is one direction. This is called uniaxial state of stress. Suppose I have a stress in this direction also. I'll call this one as a biaxial state of stress. Even if I have shear stress, I'll show shear stress something like this. Here, something like this. So this I'll call it as biaxial state of stress. If I want to represent the triaxial, that means in three directions. So you need to. So this is a plane, biaxial or plane stress. That's why I already asked you. You studied plane stress analysis. That means you might have done all these things. So in case of triaxial state of stress, you need to take a cubic element, not simply a square. You need to take it a cubic element, and you need to represent all the stresses acting on this cubical element. Then I can say that is a triaxial state of stress. So in problems, depending upon the complexity, so what we'll do is solving this triaxial state of stress problems are going to be very, very complicated. So then what we'll do is, if possible, we'll reduce this triaxial state of stress to biaxial state of stress, and from biaxial state of stress to uniaxial state of stress also. So like that, by doing so, what you can do is we are reducing the complexity so that we'll get some solution. Always it is not possible to find a solution for a triaxial state of stress. Okay, so here how I can reduce from triaxial to biaxial. So here, if I take these are the three axes, x, and this is y, and this is z. This is the triangle state of stress in all the three directions. If stresses are zero in any one direction, so that means, let us say, if I take all the stresses acting in the z direction are zero, I can remove all these things. Simply I'll consider only one plane, something like this. This is x direction and this is y direction. Then the problem will become biaxial state of stress. Even in this also, if I reduce one dimension, it will become uniaxial state of stress. That means I'll consider the stress is only in x direction. So I have only sigma x. So there are only pure shear stress also. That is also okay. So like this also. This is also uniaxial state of stress. This is also uniaxial, but this is a biaxial. So this is a triaxial. So like that, you can define the state of stress. So now when we have a complex state of stress, so infinite number of stress vectors act at any point inside the member subjected to the combined loads, as infinite number of waves can pass through a given point. So that means you can define infinite number of state of stress at a given point because of this complex loading, due to this complex loading. So each stress vector is characterized by corresponding plane on which it is acting. So that means the stress vector So generally we won't call it as a stress vector, but actually it is a tensor. Anyway, we can call it as maybe in some loose sense, we can call it as a stress vector. So stress vector means, like I mentioned here, all component of the stress. If you define all component of stress in a vector form, we'll call it as a stress vector. So that is depending upon the state of stress, whether it is uniaxial, biaxial or triaxial. In case of triaxial state of stress, you need to define 6 component of stress. Those are 3 normal stresses: sigma x, sigma y, sigma z, then tau xy, tau yz, tau zx. Like you have 6 stresses are there. Suppose if you come to the biaxial state of stress, in the z direction all the stress values are 0. That is sigma z, tau zx, tau zx, tau yz are 0. You have only sigma x, sigma y and tau xy. So like that. In case of uniaxial, you don't have y direction also, you don't have sigma y and tau xy also. You have only sigma x. So that is what we call it as uniaxial, biaxial. Or if you want to define the stress vector, only thing is, in case of uniaxial loading, you have only sigma x is your stress vector. In case of biaxial, sigma x, sigma y and tau xy is your stress vector. Whereas in case of triaxial, you need to define all 6 components. So this is what we already discussed. State of stress at a point is nothing but it is totality of all stress vectors acting on it. So that means you need to consider all stress vectors acting at a given point. Then we'll call it as a state of stress. For design purpose, it is very important to know the state of stress so as to determine the critical planes, the respective critical stresses, and relate them to the strength of the material. So always, if you are designing the component based on the strength, then what you need to do is you need to identify the first what is the critical stress value. So then generally we will design for critical stress only. So that critical stress is going to be the maximum stress always, whether it is a bending stress or normal stress, direct stress, tensile stress or shear stress, whatever it may be. We need to find out what is the critical stress means, nothing but the stress having largest magnitude, and we'll relate those stresses to the strength of the material. Then we'll get the design equation. From the design equation we can calculate the dimensions. So sometimes we'll look at some planes definition also. So because the critical stresses are identified as critical planes, those planes are nothing but sometimes you may have principal planes, or sometimes you may take plane of maximum shear stress also. Suppose your criteria is designing for the maximum normal stress, then in that case I will take a principal plane as a criteria for designing. Because in principal plane, the shear stress value is 0, only I have normal stress, and that too the normal stress is maximum. So therefore, if I want to design for only normal stress, I need to choose the critical plane is nothing but a principal plane. So on the principal plane, I need to compute the stresses. Or sometimes, if my design criteria is based on the maximum shear stress, then I need to identify a plane where the shear stress is maximum. Then I'll call that plane as the critical plane for that particular design. So then, based on that, we need to compute what is the based on that critical plane. You need to compute what is the maximum, what is the shear stress, which is the maximum shear stress, and then equate that maximum shear stress to the shear strength of the material. So from that you will get your design equation. Then if you solve the design equation, you will get the dimensions of the component. So okay, right, that's what I already told here. That is shown. I have shown that in this slide. State of stress at a point. So here this is a triaxial state of stress. If stress vectors acting on a 3 mutually perpendicular planes passing through the point is known, stress vector acting on any other arbitrary plane at that point can be determined. So that means, so what he is saying that if you know the state of stress on a 3 mutually perpendicular planes. So here, like I already drawn this cubic element and I showed you. So on these elements, if you represent the stresses acting on at each of the planes, each of the 6 planes, then from that you can easily write our stress vector acting at any plane arbitrary to these planes. So thus, to find out the stresses on any arbitrary plane, we need to use stress transformation equations. So we'll see what are those stress transformation equations. Before that, I think we already discussed this notation, how we got in case of normal stress. It is simple. The notation is sigma x, sigma y, and sigma z. That means if the perpendicular direction to the cross section is the x direction, then the stress is also in the x direction. I'll call it as a normal stress. That's why both the stress direction or load direction and the perpendicular direction is same in case of normal stress. Let us say if I take this face, this particular face here. So the perpendicular direction for this face, it is something like this, which is x direction. Then if I take the stress is also in the same direction, then I'll call it as a normal stress. That means the direction of outer normal will coincide with the direction of the loading or direction of stress. We'll call it as a normal stress. Or else, if the direction of the outer normal is different from the direction of the loading, then you will get a shear stress. So that means here, if I take this one here, this stress, here the outer normal direction is like this. The perpendicular direction to this plane is nothing but the outer normal direction. So that is like this here. But here the stress is acting in this direction. So I cannot call this stress as a normal stress. So definitely this stress should be a shear stress. Now in order to identify the notation for this, so generally we'll use tau for the shear stress. Then first letter, so I already told you in the previous class, these two letters will have two notations. One is first letter, first subscript is for outer normal direction, and the second subscript is for the stress direction. So now here for this the outer normal direction is x, and this is the direction of the stress. So here this direction is parallel to the z. So that means the stress is acting in z. So I have to denote this one as tau xz. So that's what he has shown it here, tau xz only, but it is not visible that much clearly. Similarly, if you take this here, I think it is visible. Or else if I take top face, so then I can explain it very easily here. Now if I take this top face here, so what is the outer normal direction for this? Y is the outer normal direction. That means the perpendicular direction to this face is nothing but the outer normal direction, which is y. So then if the stress is also acting in the y direction, simply I will take sigma y because it is a normal stress. Both the directions are coinciding, outer normal direction and the stress direction. That's why it is called normal stress. Why it is called normal stress? Because the stress is acting in the normal direction. That's why it is called normal stress. Similarly, now if I take this, outer normal direction is y, but what is the direction of the stress? This direction is parallel to x-axis now. So direction of stress is x direction. So therefore, the shear stress is denoted that one as tau yx. So that could be the tau yx. So on y plane, if you take here, on y plane, you have sigma y, tau yx, and similarly this stress is going to be tau yz. So you have tau yz. If I take x plane, so x plane in the sense plane perpendicular to the x-axis, that we call it as x plane. So on this you have sigma x, tau xy, tau xz. See, first two letters are same. Whatever x you got it here, even in for shear stress, x will come because this is the direction of the outer normal, which is same for all the, whether it is normal stress or shear stress, it is same. Only in case of shear stress, you have a second subscript because that the second subscript comes from the direction of the stress value or load value. So like this, you can define the state of stress. So if I am able to define the state of stress on all three mutual perpendicular planes, so you can see here, these three planes are mutually perpendicular to each other here. Mutually perpendicular means each one is at 90 degrees to the other. So then I can find the state of stress at any point using these three states of stress. So how I can done that? So for that here, maybe the whatever explanation I have given so far, that he has written here. Let us consider three mutually perpendicular planes, x plane, y plane, and z plane, passing through a point as shown in figure A. Normal and shear stress components acting on these planes are defined by something like this. So we already know the definition of all these things. The x plane for x plane, y plane. Similarly, same can be extended to the z plane also. So now, if the state of stress, when stress on one surface is 0, we call it as a plane stress. That also I already told to you. That is, out of these three planes, on these three planes, So state of stress in one direction is 0, then this is going to reduce to a plane stress problem. So that's what is stated here. Stress on one surface or 0 is called a plane stress. Then this is the figure you can call it as a state of plane stress or biaxial state of stress, you can call it as. In case of biaxial state of stress, you can say that the state of plane stress, this is, you have only stress in two directions. So that is, it may be normal stress or it may be shear stress. So here he has taken the components on the z plane to the 0. That means sigma z, tau zx, tau zy are zeros. Then we'll choose only xy plane. On this xy plane, you have only stress in either in x direction or in y direction. You don't have stress in the z direction. And also here, one more point here is, the sign convention is also very important. So there is no issue with this sigma x and sigma y. So because if the sigma x is tensile, you will take it as positive. That means if it is pointing away from the body, we will take it as positive, or else if it is acting something towards the body, something like this, we will take it as negative. Whether it is sigma x or sigma y, there is no issue. So you can easily identify if the stress is tensile, which is positive. If the stress is compressive, then it is negative. But we will face some difficulty while identifying the direction of the, while identifying whether the shear stress is positive or negative. That is somewhat difficult here, but it is not that much difficult. We can easily identify that also. How I can identify whether the given stress is positive or negative? So for that, what you need to look at is, again, like I said, while defining the shear stress, you have two subscripts, like let us say tau zx. If I take here two, z and x. In this, z is the outer normal direction and x is the stress direction. So now, to identify whether this tau zx is positive or negative, what you need to do, what you need to see that what is the direction of the z and what is the direction of x. That you need to look at it. Based on that, you can identify the value of shear stress. If both are positive, that means the z direction is z is in positive direction and x is in also positive direction. Both are positive. Then the resulting shear stress is also positive. Or else both are negative, even for that also the resulting shear stress is positive. Other than that, so one is positive, other one is negative, definitely you are going to get only negative. Or negative positive or positive negative. In for both the cases, you will get a negative shear stress. What is this? Both are positive. What is both are negative? How you can identify that here? You can see that here also. Suppose if I want to identify, this is our tau xy. So I want to identify where, so he has given in the diagram, he has given the state of stress something like this. I want to know whether this is a positive stress or negative stress. So then how I can do that? First I need to see what is the outer normal direction. So outer normal direction means perpendicular direction to this face, x face, in x direction. So here it is in the positive direction only. So your positive x here he has shown. He has shown the positive x is like this. So that means this is positive direction only. Next one, what you need to look at is in the y. So the stress direction is also in the positive y direction. That means this is positive and this is also positive. So therefore, your tau xy is positive now here. Similarly, if you take here this, okay, I'll take this normal stress and I'll take this shear stress also. I want to identify what is the sign, for normal stress first, and what is the sign for this tau xy also. Again, here also it is tau xy or tau yx, because I already told to you, if you use concept of complementary shear stress, our tau yx is same as tau xy. So that's why everywhere they will write only tau xy instead of tau yx. They will write only tau xy. So now, how I can identify the sigma y here? It is positive or negative? Anybody answer? Here the sigma y is negative or positive?
Positive, sir.
Huh?
Positive.
Why it is positive? Because it is acting in negative direction, na? So your positive y direction is something like this. It is acting in this direction. Why it is positive? It should be negative, na?
Tensile, sir. Tensile load got, sir.
Because it is tensile, you say it is positive. Oh, then what about this? This is also you are saying that tensile, right?
Yes, sir.
So, but actually that is the not the explanation here. So, like I said, negative will become positive. So now, if I take this face, what is the outer normal direction? This is the outer normal direction. This outer normal direction is in negative y. The stress is also acting in which direction? Negative y only. So both are negative. Negative into negative will become positive. So while sometimes if I take this one, I'll say the load is, this load is tensile load. We are taking this one as a positive load. But while solving the problems, what you do, you are taking the algebraic sum of the forces equal to 0. If the force is acting in this direction, we are taking positive. If the force is acting like this, you are taking negative. P minus P is equal to 0. That is the equilibrium equation, right? You are writing. And then if you want to write the equilibrium equation for this, what you need to do? In order to say the given component is in equilibrium, so then when it will be in equilibrium, the algebraic sum of the forces is equal to 0 and the algebraic sum of the moments are equal to 0. If those two conditions are satisfied, we can say that the body is in equilibrium. So now, if you apply that for this, so now how I do? I am taking this side for if the force is acting in this direction, it is positive. If the force is acting in this direction, it is negative. So then then only I am getting the equilibrium equation. These two are, if I sum up these two, I will get the 0. But even though the force is in this direction, why you are taking this one as a positive force? We are saying it is a tensile load, right? Is it tensile load or compressive load?
Tensile, sir.
So why we are taking positive, but here I am taking negative, but still we are saying it is a tensile load, positive load. Why? Because this is the reason. The load is acting in negative direction and the outer normal direction is also negative, so that's why it is tensile. It is positive. Similarly, you can extend the same concept to this also, shear stress also. Here, outer normal direction is negative direction and the stress direction is also negative. So positive x direction is like this, but the stress is acting in negative direction. So both are negative. This is negative and this is negative. Negative or negative will become positive. So therefore, whatever directions shown here, this is tau xy, it is positive only. Even this tau xy is also positive only. Even this tau xy is also positive and this tau xy is also positive. So while representing the state of stress, if you show some of the shear stresses positive and some of the shear stresses are negative, which is wrong. You cannot show that. What I mean to say here is, let us say if I show one stress, shear stress is something like this, then obviously because of this, so there is a complementary shear stress. If you have stress like this, you have like this. Then if I show something like this, so now is this body is in equilibrium for this case? If I take this is the center or pivot point here, so is it in equilibrium now? So I can say it is a positive stress here. It is also, this is also positive because this is positive direction, a positive outer normal direction and acting in positive direction. So it is positive. Here negative outer normal direction and negative direction. So this is also positive. But here the outer normal direction is positive, but the stress is acting in negative. So it is negative here. Here outer normal direction is negative, but the stress is acting in the positive direction. So therefore this is also negative. So these two are positive and these two are negative. Now is the body is in equilibrium or not? This is not in equilibrium. Why it is not equilibrium? Say if I take this point, about this point, all these stresses are creating movements in the clockwise direction. If you see all these things. So here, okay, let us say this is tau xy. Everywhere the magnitude, I'll take same magnitude, tau xy, tau xy, tau xy. But all these stresses are rotating in the anti-clockwise direction. Because of that, the body is not in equilibrium. But if I take the same thing here, so now because of this, it is creating this kind of movement. So that will be balanced by this stress. It is creating opposite movement. So these two are balanced by each other. Similarly here, because of this, if this is creating a movement in this direction, so this stress is balancing that. So that means now whatever movement is there, that movement is nullified and the total movement is going to be 0 for this. So the component is in equilibrium. So that means always important. It is important when if you have a positive stress, and all the planes you should show the positive stress only. You don't show some planes are positive stress and some planes you can't show negative stress. So you have to show in all places, all face or all planes, you have to show the positive stress. Or if it is negative, you can show negative. That means what I mean to say here is, so now I can show something like this. This is negative, then this is also negative. Then I have to show this is also negative, then this is also negative. So that means if the shear stresses are represented by like this, you have to take them as a negative shear stress values. If the shear stresses are represented by like this, you need to take them as positive. So why I am discussing all these things is later onwards we need to compute the principal planes and principal stresses. In those principal planes and principal stresses, if you substitute wrongly the magnitude, then you will get your principal stress values are wrong. So that's why you need to be careful about that. Okay, right. So then, from this, okay, this is the state of stress given, plane state of stress. Now, if I want to find out the state of stress on any other inclined plane which is making some angle theta, if I take this angle is theta with the horizontal, so now I want to find what is the stress values or what is the magnitude of normal stress. Normal stress is acting in the normal direction, and transverse direction I have a shear stress. I want to find those things. So these magnitude of these normal stress and shear stress can be found using the stress transformation equations. So we can easily derive those stress transformation equations just by calculating the forces acting in the normal direction and considering the forces acting in the shear direction. And if you write the equilibrium equations, you are going to get the resulting equations, which are nothing but our stress transformation equations. Anyway, we are not going to derive those equations straight away. I am giving all those equations because you already studied all these things. So now, for on that inclined plane, if I want to find out the magnitude of the normal stress, so this is the formula you need to consider: sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta, where theta is the inclination of the plane with respect to horizontal, plus tau xy sin 2 theta. So now, suppose if you want to calculate the stress on an inclined plane, now here this is important factor. Here, like I said, whether you have to take tau xy positive or negative. If you take tau xy positive in this equation, you will get one answer for sigma. If you take tau xy as a negative here, so this entire quantity you need to subtract it. So therefore, you will get some other value. So that means if you don't know the sign convention properly, you are not going to get the proper value for the sigma value. Even now, not only for sigma value, even for shear stress also you will get a wrong value. So that's why here the sign convention is very important. Of course, sigma x, sigma y sign we can easily identify because whether it is tensile or compressive, we can easily identify that. But whereas only in case of shear stress there is a little bit of confusion. But now I explained that how to find the direction, whether it is positive or negative for this also. Already told to you. The only thing is we need to look at the outer normal direction and the stress direction. Both are negative, you will get plus value. Or both are positive, also you will get plus. In other two cases, you will get a negative value. So now, next criteria what we need to do is, okay, this is the expression for the normal stress. Similarly, you can get the expression for the shear stress also if we equate the components. But here, our intention is not to find what is the magnitude of the normal stress on inclined plane. So our intention is we will design always will design the components for a critical stress values. So that means those critical stresses are occurring on a critical plane. So our intention is we want to find out what are those critical planes. So further to find the critical planes, like I mentioned already, sometimes we'll use the principal planes for the design criteria, or plane of maximum shear stress will use the design criteria. So the plane of maximum normal stress, we'll call it as a principal. The definition for the principal plane is nothing but plane of maximum normal stress. That means the plane where the maximum normal stress occurs, we'll call it as a principal plane. Of course, the shear stress is 0 on the principal plane, and also sometimes we'll use plane of maximum shear stress also. So now to identify that, what I have to do is, here the maximum normal stress, how I can identify it, I got an expression for the sigma. So now if I want to find the theta value where the critical plane occurs or where the principal plane occurs, for that what I need to do is I need to differentiate the sigma with respect to theta and I need to equate this one to 0. If I do that, if I simplify that, I'll get this is the equation for the definition of the principal plane. This is the equation you are going to get. So anyway, I am not deriving all these things because you already studied and also that is not part of our course also. Just, but we require these relations to solve the problems. That's why we are reviewing those relations. So now, with this, using this relation, you can easily get the plane of maximum normal stress. And also here also that is also important. Sign convention is important. Tan x tau xy. If you take plus here, you will get theta value one value. If you take negative value here, you will get another theta value. So that means which one is correct you need to identify properly. Whether it is positive value is correct or negative value, that is only based on how you identify the value of tau xy. So once I know the plane of the maximum normal stress, then I can find out what is the value of that maximum normal stress. So that can be done. So then those normal stresses will call it as a principal stresses, and the magnitude of those principal stresses are given by these are the formulas. So that's what I written here. Two principal planes which are perpendicular to each other. Always these principal planes are in case of biaxial state of stress. Remember, we are discussing about biaxial state of stress. In case of biaxial state of stress, we need to define three principal planes. So that is why using three principal planes only you can define the state of stress. In case of triaxial state of stress, in case of biaxial state of stress, you need to define two principal planes. Whether it is biaxial or triaxial, always these principal planes are perpendicular to each other, mutually perpendicular to each other. So now, if you consider the biaxial state of stress, so one has the maximum normal stress, another one is also maximum, but only thing is it is a compressor. That's why we'll call it as a minimum value. So those two planes we'll call it as a principal planes, and shear stress on that principal plane is 0, like I already told you. That is, the shear stress component acting on these planes is 0. Then the magnitude of those two principal stresses. So maximum principal stress will be denoted by sigma 1 and minimum principal stress will be denoted by sigma 2. So and these are the formulas to compute those maximum normal stresses. So sigma 1 is given by, this is a relation. This is a relation for sigma 1 and sigma 2 can be calculated this one. So that means only here it is plus is there for sigma 1, here you have negative is there. Other than that, all the terms are same only here. So once I identify that, then I'll use this maximum normal stress for my design criteria. Similarly, in some instances, we want to compute the maximum shear stress instead of sigma 1 and maximum normal stress. Suppose if the shear stress is my design criteria, in that case I need to find out what is the maximum shear stress in the component. So for that, this is going to be the formula for the maximum normal stress, or else this is the maximum shear stress value. So from these two relations, you can write this tau max as sigma 1 minus sigma 2 by 2 also. Sigma 1 minus sigma 2 divided by 2 also. So that means if I take these two expressions, if I subtract sigma 2 from sigma 1, what happens? This will cancel out. Only thing is this one you will get. So divided by 2 means it is, if I add these two, I will get 2 times this one. Divided by 2 means I will get only this quantity. So that is nothing but your maximum shear stress. See here, if you look at this tau max, here you have plus or minus sign only. So that is, the plus value is same, even the minus value also same. But only thing is, there is a change in the direction. Like I said here, the stress can be, shear stress can be positive. If you represent this one like something like this, it is positive. If I represent something like this, it is going to be negative. That is the only difference. But magnitude wise, they are same. So here you can see that the maximum shear stress value is same, whether it is positive or negative. But only thing is there is a change in the direction. So now using this equation, I can calculate the maximum shear stress. Once I have maximum shear stress, I can use this one as my design criteria for designing the component. So now, so far we discussed how to identify the critical planes, Then we are in a position to find the magnitude of the stresses on those critical planes. So if I take a principal plane, then I need to compute what are the principal stress values. If I take a plane of maximum shear, I need to compute what is the maximum shear. So there is another way of, without using these calculations also, if you draw more circle method is also there. Using more circle concept also, you can find out what is the magnitude of principal stresses as well as maximum shear stress also. Anyway, whatever approach you follow or you adapt, but only thing is you need to compute as per your requirement, you need to compute the stress values, whether you require a normal stress value or maximum normal stress value, or we require maximum shear stress value. So then, based on that only, we are going to design the components. So now, based on whether you are designing the component, whether based on maximum normal stress or maximum shear stress, there are different failure theories. We call these failure theories as elastic failure theories. So, out of those basic failure theories, they are based on either maximum normal stress or some are based on maximum shear stress. So we'll discuss those things in the coming class. Maybe in the next class we'll discuss about those theories of failure or theories of elastic failure. Then how we can design the component based on those theories of failures. So we'll see those things in the coming classes. So today I'll stop at this point. Still we have 5 more minutes time left with us. So if you have any doubt or any clarification or any query, then we'll discuss those.
Sir, previous slide ఒకసారి చూపించండి సార్.
Previous one, this one or previous one? This one?
ఇదే సార్.
Then, okay. What is your doubt in that?
నోట్ చేసుకోవడానికి సార్ ఫామ్.
Note చేస్తున్నావా? Already okay. If you want, note it down. No problem. No issue. So this is the expression for the normal stress on that plane, and this is the expression for the shear stress on that inclined plane. Now, if you differentiate this one with respect to theta equated to 0, you will get the position for the normal stress. Similarly, you can differentiate this one with respect to theta and equated to 0, you will get the plane of maximum shear also. And also, maybe I have not mentioned here, there is some relation between plane of maximum shear and plane of normal stress. What is that relation? Anybody knows that? Relation in the sense of orientation. In the orientation, there is a relation between this plane of maximum shear and plane of maximum normal stress. What is the angle between those two?
90 degrees.
90 degrees. 90 degrees wrong, amma. 45 degrees. Why it is 90 degrees?
More circle hoga sir.
More circle నువ్వు ఏం చేస్తావు? Each angle you have to represent it by 2 theta కదా. In the more circle,
yes,
what you do? Sigma 1, sigma 2, they are perpendicular to each other అనుకున్నాం కదా మనం.
Yes,
Sigma 1, sigma 2 perpendicular గా ఉంటాయా? Biaxial state of stress కదా sigma 1, sigma 2 అంటే నువ్వు స్ట్రెస్ ఎలిమెంట్ చూపిస్తే నువ్వు చూపించేది ఎట్లా చూపిస్తున్నావు దాన్ని? This is sigma 1 direction, this is sigma 1 and this is sigma 2 అంటూ అంతేనా? Right?
yes sir.
So what is the angle between these two? 90 degrees. But if you represent that on a more circle, what you are doing, you will show it as something like this. So this is sigma 1 and this is sigma 2 direction. So they are at 180 degrees.
180.
So always in more circle you will represent 2 theta, not theta, because in your equations you have 2 theta things. 2 theta is here. Every angle, see here, even tan theta, in this expression also you have 2 theta. That's why in more circle we will show the angle double. So here, this is the plane where your normal shear stress is 0. This is the shear stress is 0 plane. So that means you have sigma 1 in this direction and sigma 2 is in this direction. Then this is the maximum shear stress plane. So here the radius of the circle is nothing but your maximum shear stress only. So then what is the angle between these two? 90 degrees here. This is the principal plane and this is the maximum shear plane. But on more circle we are showing the 2 theta angle, but we are interested in theta angle. So therefore always it is 5/4 only. Or
Okay.
else, if you take a simple case, if you take a simple tension test, MOS level మీరు టెన్సైల్ టెస్ట్ చేశారు కదా,
Yes, sir.
చేసే కదా. ఇప్పుడు ఈ కాంపోనెంట్ రాడ్ ఒకటి తీసుకొని నువ్వు దాని టెన్సైల్ లోడ్ అప్లై చేసి అంతేనా, యూనియాక్సిల్ లోడ్. దాన్ని వీల్ కాల్ ఇట్ యాజ్ యూనియాక్సిల్ లోడ్ బికాస్ వీ అప్లైడ్ ద లోడ్ ఇన్ ఓన్లీ వన్ డైరెక్షన్. నీకు ఎలా ఫెయిల్ అయింది నీ కాంపోనెంట్ అబ్జర్వేషన్, అది రాడ్ బ్రేక్ అయింది కదా. ఎలా బ్రేక్ అయింది? ఇట్ బ్రేక్ సంథింగ్ లైక్ దిస్. ఆ రెండు ముక్కలను చూసినంటే యూ కెన్ అబ్జర్వ్ దట్ దెర్ ఈస్ ఎ ఫెయిల్యూర్ సంథింగ్ లైక్ దిస్. దిస్ ఫెయిల్యూర్ ప్లేన్ ఈస్ గోయింగ్ టు బి 45 degrees. Maybe you have not measured all those things. So therefore this is the plane where it is fracturing. So the shear stress is causing that kind of failure. So it is at 45 degrees only, even though you are applying a normal load. So but your component is failing in shear there.
Okay, sir.
Okay, right. So any other doubt? Somebody is put some. Okay, yes sir. Okay. Okay, and doubt unda? Ee doubt ledante then you can leave, no issue. If you have any doubt, we'll discuss. Otherwise, I'll also close the class.